All right, so what I'm going to talk about is a concerns some mathematical aspects of actually numerical methods for approximating Navier-Stokes equations in dimension 2. But yeah, but let me begin with a couple of observations that to experts will be trivial, but still. So the thing that I believe you should have in mind to understand my motivation in taking a look at what I'm going to talk about today is the following. The phenomenon is the following. You have a bounded domain in dimension 2, and you're considering a incompressible flow. So what happens is that in close to the boundary, the effect of this obstacle that is the boundary is the generation of turbulent effects. Concretely, what you see is that close to the boundary, one can observe the formation of small vortex-like coherent structures that then coalesce and evolve, and then one would like to describe. So I will not be talking about turbulence. I will not be talking about cascades of energy and entropy, which is the true phenomenon. But instead, I will just focus on certain kind of approximations of the 2D Navier-Stokes equation that I believe could give some insight in explaining this kind of phenomena. So, all right. So, concerning the Navier-Stokes equations in dimension 2, but more generally Navier-Stokes equations, one could divide the methods for solutions in roughly into different approaches. So perhaps the mainstream one is Eulerian methods, which consist in discretizing the fluid, looking at the velocity field on a lattice, on a fine mesh, and then proceed to evaluate the evolution by finite differences, or projecting in Fourier space, or looking at wavelets decompositions. And the other one, and actually these methods differ just in how one chooses to discretize the fluid, and the other one is Lagrangian methods. So instead of looking at the velocity field, one looks at vorticity field, which is just the curl of the velocity. So we are in dimension 2. This will be a scalar field, and one discretizes the vorticity field and looks at how particles of a vorticity, and those are the ones called point vortices, evolve under the flow of Navier-Stokes equations. So why should one consider the Lagrangian approach, especially since I believe we are used to see direct numerical approximations of Navier-Stokes consisting in very large finite differences methods. Since nowadays our computers can manage those kind of simulations. Well, what happens is that starting with the works of Chorin in the 50s, the point vortex method for approximating Navier-Stokes turned out to produce very good qualitative approximations of the fluid dynamics, in the sense that even with a very rough discretization, the qualitative look of the simulation is close to a fluid dynamic evolution, and especially close to the envisaged case, right? So when the viscosity nu is small, the flow is dominated by the advection of the velocity field. This turns out to be the case. All right, so what is the point vortex method? Essentially, one considers a stochastic interacting particle system. So let me give you a rough description of what is going on. In red, there is an interaction kernel, and that is the thing that models the nonlinear interaction. That is the nonlinear term in Navier-Stokes equations. The noise that acts on single particles will model the viscosity, corresponds to a diffusion of those particles. And then, in order to make this an approximation of Navier-Stokes, one should consider a mean field limit of these particles. Namely, one can take a look at the empirical measure of the particles and send n to infinity, but also just consider the marginal distribution of one single particle, and this empirical measure will converge to vorticity that, as I was saying, is simply the curl of the velocity, which is convenient in 2 dimensions, because if you rewrite the dynamics of Navier-Stokes, the pressure goes away, and you're left with this equation that only involves the parabolic Laplacian term, and then the advection by the velocity field induced by vorticity itself. So, all right. So, what about the boundary conditions? Yeah, let me go back. So, the boundary conditions are no-slip conditions. The fluid should stay still in correspondence to the boundary. And right, so if you want to model the equation with finite differences, this is rather easy to impose. But what happens for the point vortex method? It turns out that it is quite difficult to impose no-slip boundary conditions to a point vortex method. To be precise, the interaction kernel of vortices can easily encode the fact that the fluid should not go outside of the boundary impermeability, and this is done simply choosing properly the green function of the Laplacian in the interaction kernel. But it is very hard to decide what one should do so that the tangent velocity of the fluid is 0 at the boundary, and this is from the point of view of point vortices what should create new vorticity, right? Because in order to impose this condition, the only possible choice we have in this model is to create new vortices, so to compensate the fact that the bulk of the fluid produces tangent velocity at the boundary. Oh, so in order to solve this problem, of course, this was clear from the beginning to people approaching the vortex method. First of all, Chorin, and here it is how Chorin attempted to solve, at least from the point of view of numerical simulation, this issue. Actually, his first attempt consisted in simply creating vortices very close to the boundary. But then again, he was facing an issue. So in doing the numerical simulation, you don't actually have idealized vortices. You should consider small blobs corresponding to the fact that positions of vortices actually stay on a fine mesh because of numerical discretization, and so this mathematically has to correspond to regularizing the interaction kernel at some small distance. So instead of delta Diracs, you should think of vortices as small vorticity blobs. But creating those blobs close to the boundary made everything unstable, and so he proposed instead to create close to the boundary, where close, this y infinity that measures the width of the boundary layer, has to be chosen empirically. Close to the boundary, what happens is that the algorithm creates small vortex sheets. Instead of blobs, one creates lines of vorticity that compensate the velocity induced by the bulk of the fluid close to the boundary. And then those vortex sheets will evolve in time in the following way. So in order to model viscosity, they will follow a Brownian motion, a diffusion process that can bring them again at the boundary, where they will be bounced back, or inside the bulk of the fluid, where they are converted into blobs. Still, at this transition between sheets and blobs, Turing was observing instability of the simulation, and so this was not even numerically a complete solution of the issue. All right, so instead of looking at of trying to impose that the velocity of the fluid vanishes at the boundary, one can take as a proxy the following system. So as I was saying, in the interaction kernel, one encodes the fact that the boundary is impermeable, and then one replaces the condition of the velocity being tangent to the boundary with Neumann condition to vorticity, which is completely unphysical. It is just a proxy, and I will try to explain why this can be a reasonable choice. The point is that this rate g in the Neumann condition should depend on vorticity omega, on the whole vorticity also inside of the fluid. So this is going to be a non-local, non-linear function of the whole vorticity field. And right, so just to mention a couple of examples in which this idea was brought on. In both Eulerian settings, so when the simulation is then run by finite differences, and this is a work of Benfatto, Pulvirenti, and other collaborators. And then in the Lagrangian setting, there were people attempting to prove that, from the mathematical point of view, one can perform a good approximation of this system, but it remains open a rigorous mathematical proof that one can put together this Neumann approximation with the correct rate g in order to simulate the true system. And yeah, so there is an intuitive idea that then was transformed into algorithms proposed by Kotet and Koumoutsakos in the 80s, consisting in a two-step algorithm. And yeah, so this is how the Neumann boundary condition can be used or rather, yeah, can be used as a proxy for the true boundary condition. So during the first step of the time iteration of the simulation, one simply solves Navier-Stokes equations with null Neumann boundary condition, and this is easy to impose on point vortex methods because you simply ask that vortices are bounced back elastically when they arrive at the boundary. And then, in the next step, if you are able to approximate a non-zero Neumann condition, you run again the simulation, still on the same time increment, but using as the source g for the Neumann condition the the velocity field, or rather this blue, rather complicated function of the velocity field of the previous iteration. All right. So our contribution, and by ours I mean of myself and Mario Maurelli and Eliseo Luongo, was to focus on step 2, namely the approximation of the Navier-Stokes system with this unphysical Neumann condition in which the source is prescribed, in the hope that this can be then combined in order to give a rigorous proof of the convergence of this kind of algorithms to the Navier-Stokes system. So, right, we first applied, in order to have a uniform approximation of the solution, we took the approach of kernel smoothing that in this context was first introduced by Franco and Cristian Oliveira and Maria Simon some years ago. They were studying the same Navier-Stokes system, only without boundaries. And what we did, yes, so what we did was to consider a smooth interaction and smooth point vortices, where the smoothing is obtained by the convolution with Neumann hit kernel. And this is, I believe, a rather important thing, because the Neumann hit kernel works well with bounded domains, solving the issue that Chorin had when creating vortex blobs corresponding to the boundary, because the hit kernel automatically encodes good behavior at the boundary. And right, so and we both use this hit kernel to smoothen the interaction and to regularize the empirical measure, and then in order to model the generation of vorticity at the boundary, we consider vortex generation in the following way. So remember, one has this kind of vortex vortex generation rate prescribed a priori. So now in this step 2, that is fixed, right? So it is a complicated function of the previous iteration, but one can regard it as a fixed rate that is prescribed, and so one can discretize this rate looking at local averages of this rate on the boundary of the domain, and create vortices at the center of these small squares, small elements of the grid with which we discretize the rate, and then let vortex evolve inside of the domain. So there is no distinction between the boundary layer and the bulk of the fluid. And right, so I can conclude with a statement, which is simply what I was talking about. So one can consider a smooth empirical measure of the vortices. Now the xi's are single positions of the vortices, and the empirical measure has to take into account the fact that not all the vortices will be alive at any moment, because some of them are created later, and this empirical measure converges